Hello everyone, we are starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you, the viewer, want to ask questions and get answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule of the lectures, join our Telegram channel. A floor of the size n by m is given. It needs to be covered with rectangular parquet, where each and every board is of size 1 by 2. The boards can be laid both vertically and horizontally, which provides flexibility and versatility. It is absolutely necessary to find the corresponding number of ways to lay the parquet under the given constraints and conditions. So for example, we have a floor of size 2 by 3, and we will look at the different possible ways to lay it, for instance, in various patterns and arrangements. There will be a total of 3 of them here. That is, you can place a vertical board on the left or right, or they can all be vertical. A primitive way to solve such a problem is to iterate through all possible layouts in a detailed and comprehensive manner, meaning going through all the address codes in detail, and if the current one is empty, trying to place a board. This is
Want to become a great programmer? Subscribe to our Telegram channel.
how it actually happens, to ensure clarity and understanding for each step. We will have matrices, again based on the input data, where there are n by m, and for each board there will be a status for each position, which can be either 1 or 0. 1 means that something is already placed there, and 0 means that nothing is placed there yet. Accordingly, we will recursively start the process for each step and iteration to make sure that the process is clear and easy to follow, and to ensure that every step is well understood. In the very first cell of our grid, we will attempt to place a board. We have 2 options for placing the board, either like this or like that. If we decide to place the board horizontally, it means that we will occupy these 2 adjacent cells with 1s. This placement strategy is crucial because it determines how the rest of the board will be filled. By placing the board horizontally, we ensure that these 2 specific cells are marked and accounted for, which is an important step in our overall plan. This method helps us systematically cover the grid without missing any cells. Accordingly, we recursively change the value to 1 in these 2 specific positions within the matrix, and then proceed to move to the next cell in the sequence. This process is repeated for each cell until the entire matrix has been processed. Here we see that the unit is currently occupied, meaning that we cannot place a board anywhere at this moment. Therefore, we will continue to proceed recursively with our current approach and strategy, ensuring that we carefully consider each step. We will go into this cell like this, first moving across the rows one by one, then descending to the second row, and we will continue moving from left to right and top to bottom. Here we will have a value of 0 initially, and here it will also be 0. Accordingly, we will try to place here and here, and so we will gradually descend recursively until we reach this point. Initially, we will go into this cell like this, first moving across the rows one by one, then descending to the second row, and we will continue moving from left to right and top to bottom. Here we will have a value of 0 initially, and here it will also be 0. Accordingly, we will try to place here and here, and so we will gradually descend recursively until we reach this point. Then we will backtrack recursively, because we have counted everything here, back to this cell, in this process, step by step, very carefully. Since we have obtained a value for this type of layout, that is, for the value when we place a board horizontally from position 1,1, in this specific context, we erase the Boolean value here, replace it with 0, and then we set TFSP to 1 here and 1 here. Specifically, in this case, we essentially set TFSP to 1 here and 1 here. Therefore, in essence, in this particular instance, that is, now we start from the position where there is a vertical board, and then we proceed in exactly the same way. That is, we will recursively enter, set a Boolean value, count, return, and undo this Boolean value. That is, first we set it to 1, and then we set it to 0 when we return, and try to place it in a different way. And accordingly, how this will work for us, since we will have recursion, first we check for what we can do is move on to the next row. Then we check if the enclosing cell is occupied. If it is, we move to the next one, meaning we recursively move to j+1. Otherwise, we try to place a horizontal board and a vertical board. As I mentioned earlier, we recursively set Boolean values to true, go through all the recursions, return to the next state, undo everything, and do the same with the vertical board. This check is necessary so that we can attempt to place the vertical board. Additionally, it is important to note that this process ensures that we are thorough in our approach. By doing so, we can be confident that we have explored all possible options. This methodical approach is crucial for the success of our task. Therefore, we must be diligent and precise in our actions. Well, if it somehow works out, yes, to look like it's somehow in Python. And just like in C++, essentially, in a way that is very similar, basically, it's all done quite cleanly and effectively in pseudocode. The primitive solution is clear. It works here purely through brute force. It will have an incredibly high complexity. Samir, even now it's hard to remember what the complexity of TFSP will be, but in the worst case, it's actually quadratic. In the very worst case, if we're lucky, it could be something larger, because recursion will really be a significant factor here. It might even be 2 to the power of n times m. That's the feeling I get, and of course, it doesn't suit us. Not only because it will simply work slowly, but also because there will be overlapping states. That is, we will have a situation where in a situation where the cells are occupied like this, we can reach this state in several different ways and then recalculate it. Therefore, this solution will not be suitable for us in 2 different ways. And accordingly, dynamic programming will be required in this context for optimization. For this, we will essentially use a profile. What exactly will actually be considered a profile here? There will definitely indeed be an extreme, not fully covered, string. It will start from the current position. That is, since our green cells are not painted, it means the remainder of the current string and the part of the next string that was before, this position according to the stops. And we will move with such profiles, meaning we will try to transition from the profile located in this cell to this cell with some new profile. Thus, we will calculate the value only for optimal positions. Accordingly, we will represent this in the form of a bit mask, where 0 represents an occupied cell and 1 represents a free cell. So how will this mask be filled? That is, how is it obtained? The right bit for us will be the leftmost cell, while conversely, the left bit will be the rightmost cell in the table. The task will be to determine the number of ways to completely lay a section of the floor up to a given cell, under the condition that the profile for this cell is defined by the mask. Accordingly, dynamic programming will be built forward in a comprehensive, detailed, and thorough manner. We will attempt to place the board in the current cell, either vertically or horizontally. That is, in order to proceed, we have the following options for transitions in the current scenario. The first thing is that we already have something in this particular cell, which means we move on to the next cell while updating the mask. For instance, if our mask looked like this, we would have the values in the mask as 0, 0, 1, 0, 0, 1, 1. When making the transition, the mask updates to 0. 0, 0, 0, 0, 1, 1, 1, 0. In the second case, if we place the board horizontally, then when moving to the next cell, the previous cell in the new mask is set to 0 because we are transferring the last cell to the next row. It was here, and now in this particular cell. Now we are using it here, and plus 1g, so there will be 0, in other words indicating that it is still free, while g plus 1 will already equal 1, which means it is already occupied due to the horizontal board. The third method is to place it vertically. In this case, when moving on to another next cell, we will have g plus 1 equal exactly, just simply only precisely, specifically, absolutely, definitely, certainly, undoubtedly, unquestionably, undeniably, surely, clearly, obviously, evidently, plainly, distinctly, unmistakably, unambiguously, unequivocally, patently, manifestly, self-evidently, conspicuously, transparently, overtly, visibly, perceptibly, discernibly, noticeably, observably, recognizably, identifiable. And all of this intricate and detailed process will be cleverly and efficiently built using fundamental bit shifts. Accordingly, essentially to begin with, what types of bit shifts are there? There are circular cyclic shifts, and there are non-circular logical bitwise shifts. Here, the bit shift will be arranged in such a way that if we move right or left, what was in the original position is simply erased, regardless of whether we are going right or left. If we had a cyclic shift, it would just wrap around in a loop, and the cells would not be erased anywhere. Here, on the contrary, if we perform a left bit shift by 3, these two ones will shift 3 positions to the left.
Want to become a great programmer? Subscribe to our Telegram channel.